Okay, let's wrap up Chapter 3 on calculations with balanced chemical equations. We'll start with this equation, which is not boron, carbon, and sulfur, okay? But it's 2 pieces of bread and 1 piece of cheese together make a sandwich. Okay, we're not going to worry about getting more complicated than that right now. We will get more complicated when we're doing this with chemicals. So, if we look at this, y'all, if I told you, okay, what if you have 4 pieces of bread and you have a whole lot of cheese? Well, how many sandwiches could you make with 4 pieces of bread? And y'all know that you could make 2 sandwiches. And you know that by looking at the ratio of the equation, okay? And you're not thinking through it this much because it doesn't require that much thought. But you're using this ratio that I'll make 1 sandwich for every 2 breads. And so when I say, okay, you have 4 breads, you're considering the ratio from this balanced equation. I'll make 1 sandwich for every 2 breads. See how the breads will cancel, and I'm left with my answer in sandwiches. And this math, 4 times 1 over 2, gives you the answer of 2. Okay. Now, what if, in a separate scenario, what if I told you, we're always focusing on this balanced equation. What if I told you that you have a whole lot of bread and you have 4 pieces of cheese? Then my question, how many sandwiches will you make? Is the answer still 2? If I start with 4 breads or 4 cheeses, will I always make 2 sandwiches? No, because the balanced equation says I'll make 1 sandwich for every piece of cheese. So if I start with 4 cheeses, the answer is I'm going to make 4 sandwiches. So it's not the same answer. If you're starting with the same amount, but of different reactants, you're not going to get the same answer every time because it depends on how those reactants are used to make the product. Okay? Now, let's consider one more situation. Okay, so here's like situation number 1. Here's number 2. This is a whole new scenario. What if I had, again, same balanced equation of 2 breads and 1 cheese makes a sandwich. What if I tell you that I'm starting with 4 breads and I have 4 cheeses? How many sandwiches will that make? I want you to stop and think about it. If 4 breads makes 2 sandwiches and 4 cheeses makes 4 sandwiches, then if I have 4 of both, will I make a total of 6 sandwiches? No. The answer is 2 sandwiches. Okay? Because I can only make the smaller number of sandwiches. The smaller amount of product is what I can make because bread is known as my limiting reactant. The limiting reactant is the reactant that I'm going to run out of. Because see, once I have these 4 breads and I make 2 sandwiches, I'm not going to have any more bread left. I'm not going to run out of cheese. 2 sandwiches is only going to require 2 pieces of the cheese, so I'm going to have cheese left over. It's not my limiting reactant. In this situation, the cheese would be the excess reactant. Okay, because I don't run out of it. I have some left that can't react. Okay, and no, you cannot double up your cheese on your sandwich because it always has to be made 2 breads and 1 cheese. Okay, now let's apply this concept to balanced equations. And when it seems like it's getting like I'm losing you with the balanced equations, come back to look at the bread and cheese example. So let's write a balanced equation for the reaction of silver nitrate and hydrochloric acid to make silver chloride and nitric acid. So pause the video, take those words, write the formulas, and write a balanced equation for it. And then when you start the video back, you can check your answer with what I write, which is what you're doing now. So silver nitrate and hydrochloric acid make silver chloride and nitric acid. Okay. Now, I'm going to tell you now that all of this is aqueous except for the silver chloride. How do I know that? We'll talk about that in chapter 4. Okay, so hopefully we'll be all back together next week, and I'll show you how we know that. And did you guys balance the equation? You should find that it's already balanced. Okay, so what I want to do, first off, is I'm going to give you some numbers, and we're going to do some calculations with this like we did with the bread and the cheese. Do you see that this whole reaction is 1 silver nitrate and 1 hydrochloric acid make 1 silver chloride and 1 nitric acid? It's simple. So if I tell you that I'm starting with 0.587 moles of silver nitrate and I have a whole lot of hydrochloric acid, then how much silver chloride would I make? Okay, the answer is 0.587. Of the silver chloride, because one of these makes one of these. 1 silver nitrate makes 1 silver chloride. The math you're doing for that, because again, that's going to be important when it's not all 1 to 1 to 1. If we start with 0.587 moles of silver nitrate, what units do we want to cancel? Moles of silver nitrate. What did I ask you for? I asked you for moles of silver chloride. And the balanced equation is a 1 to 1 ratio. Those numbers come from this, 1 and 1. And so the answer is 0.587 moles of silver chloride. So in this scenario, we're going from moles of one thing, I'm going to call it A, it's whatever you're given in the problem, to moles of B, whatever you're asked for. So in this example, the A is the silver nitrate, the B is the silver chloride, and how you go from moles to moles is to use your coefficients from your balanced equation. Coefficient ratio. That's what this is. It's a ratio of your coefficients. Okay? Now, what we were working on last week was converting moles to grams and grams to moles. We did that a lot with combustion analysis and with the percent composition of compounds. And so you guys know that when you're in the lab, we don't have any equipment that will measure out moles. What we measure out in the lab is grams. And we can use our periodic table and our molar mass to convert to moles. So we're going to add to either side of this equation that we can convert from moles of B to grams of B. And we can also start with grams of A to moles of A. Okay? Hang in here with me. How do you convert from grams to moles? You divide by the molar mass. Again, we were doing that last time. How do you convert from moles to grams? You multiply by the molar mass. Remember, the molar mass is when we add things up from the periodic table. The molar mass of what? Well, if you're doing this, grams of A to moles of A, you're looking for the molar mass of whatever A is. If you're going from moles of B to grams of B, you're looking for the molar mass of whatever B is. Okay, so this flow chart, copied more than what I wanted to. This flow chart can be used for any equation that we're doing with stoichiometry. You just have to determine where you're going to enter the flow chart at. So if I told you guys that aluminum and oxygen combine, so aluminum and oxygen are your reactants. So write them in chemical terms, aluminum and oxygen. So you would write aluminum, and you guys know that's a solid, and oxygen, which is O2. Remember your diatomic elements, okay? Now, when aluminum and oxygen combine, what are they going to combine to make? Can you name the compound that forms when aluminum and oxygen combine? You should be able to name that they will combine to make aluminum oxide. And if you can name the compound, you can write the formula for the compound, because aluminum oxide is Al2O3. Swap and drop. Okay, now all that you should have been able to do. Aluminum oxide is a solid. Ionic compounds are always solid unless they're in solution. Now balance that equation. And you should have been able to quickly balance the equation to get that, okay? If you were struggling to get there and it took you more than 30 seconds, then you're going to have to practice balance an equation. Guys, can y'all see how much this is building? What we're using here, we're not even to the new stuff yet. We're just practicing. This is all old stuff. Writing formulas, balancing equations. Now we're ready to do some of these calculations with it. So, let's calculate the mass of aluminum oxide produced when 3.84 grams of aluminum reacts with excess oxygen. So we're starting with 3.48 grams of aluminum. The problem tells us we have a whole lot of oxygen. That's our excess. And we're asked to calculate how many grams of aluminum oxide we'll make. So we're starting with grams of aluminum. We're starting here, grams of A. We're asked for grams of aluminum oxide. We've got to get to the end of this flow chart. So we're going to start with 3.84 grams of aluminum. We're going to set up first this conversion. A mole of aluminum is 26.98 grams of aluminum. That number comes from the periodic table. At this point, man, y'all erase that. Because I wrote it wrong. It should say a mole of aluminum is 26.98 grams of aluminum. That makes more sense, so that grams of aluminum will cancel. Okay? On this step, y'all, where you're doing the molar mass step, always use 1 mole of your stuff. 1 mole of aluminum is 26.98 grams. On this step, the molar mass steps, do not use the numbers from the equation, from the balanced equation. In other words, don't use the 4 from the balanced chemical equation. You're going to use those numbers here on the next step, which is where we're at. Because the balanced equation tells us that 4 moles of aluminum will make 2 moles of aluminum oxide. We wanted moles of aluminum to cancel. The question asked about aluminum oxide, so that's how we knew what to put on the top. And the numbers, the 2 and the 4, come from the balanced equation. So this step is this conversion. Finally, in order to get all the way to grams, we have to go from moles of aluminum oxide to grams of aluminum oxide, and that's where we use our periodic table to do the molar mass of aluminum. There's 2 aluminums times 26.98. And so for the molar mass of aluminum oxide, I got 101.96 grams, the 2 aluminums and the 3 oxygens. And then at this point, the moles of aluminum oxide cancel, and we're left with an answer in grams of aluminum oxide, which I'm punching in now. I got 7.26. For my answer. Okay. Okay, let's do another one. Let's change equations. This time, let's combine magnesium and oxygen. So write the balanced equation for the combination of magnesium and oxygen. Magnesium and oxygen combine to make magnesium oxide, which would be MgO, because magnesium's +2 and oxygen's -2. And then I have to balance that equation. So a 2 on Mg and a 2 on MgO, and it's balanced. Let's calculate the mass of MgO produced when 1.68 grams of magnesium combines with 2.08 grams of oxygen. So calculate the mass. How many grams of magnesium oxide will I make when 1.68 grams of magnesium combines with 2.08 grams of oxygen? This problem is different from the one we just worked. It's different, but it's very similar. Notice in this problem, I give you 2 numbers. I give you a mass of the magnesium and a mass of the oxygen. If you look at the one we worked previously, I only gave you 1 number. I only told you about the mass of aluminum and said you have a whole bunch of oxygen. So what I was really telling you in this first problem is that since I'm limiting your mass of aluminum, that's going to be your limiting reactant. That's what you're going to run out of. But this one, I'm not telling you what you're going to run out of. So this is a limiting reactant problem. Anytime I give you an amount for each reactant, it's a limiting reactant problem. You're going to have to figure out which one's the limiting reactant. There's a lot of different ways to do that. The way I'm going to focus on today is I want you to use this flow chart. Grams of A to moles of A to moles of B to grams of B. So I want you to do each of these numbers. I want you to take the 1.68 grams of magnesium, grams of A, First convert to moles of A. 1 mole of magnesium is 24.31 grams of magnesium. That's grams of A to moles of A. Now I want you to go to moles of B. The B is the magnesium oxide here because that's what I'm asking you for. And the balanced equation tells me I'll make 2 moles of magnesium oxide for every 2 moles of magnesium. That gets me to moles of B. Go from moles of B to grams of B. Remember, the B in this equation is always magnesium oxide. That's what I'm looking for. A mole of magnesium oxide is 40.31 grams because I have to add up 1 magnesium and 1 oxygen. Magnesium's 24.31, oxygen's 16. And I get 2.79 grams of magnesium oxide. Okay, so guys, do you see that I worked the whole flow chart? Grams of A to moles of A to moles of B to grams of B using this number. Now I want you to do the same process. Moles of A to grams of A to moles, etc. The same flow chart using this number. So start with 2.08 grams of oxygen. It's not going to be the exact same numbers because you're starting with oxygen this time. I want you to pause the video and try to fill that in. Then start the video back and see if you did it correctly. Okay, so now you're starting the video back, and the first thing you did is you said a mole of O2 is 32 grams of O2. O2, so 2 times 16. Then you said the balanced equation, I'll make 2 moles of magnesium oxide for every 1 mole of O2. Because remember, the magnesium oxide is what I'm looking for. It's the B. It's my answer that I'm working towards every time. And then you said a mole of magnesium oxide is 40.31 grams of magnesium oxide. And this time I got 5.24 grams of magnesium oxide. Okay, let's look at it. Calculate the mass of MgO produced. I'm about to jump back to our bread and cheese. Okay, I'm going to jump slides when we were here. In this last situation, I told you you've got 4 breads and 4 cheeses. How did we come up with the answer of 2? Remember, we said, well, 4 breads will make 2 sandwiches. 4 cheeses will make 4 sandwiches. The smaller amount of product is the right answer because it tells me what my limiting reactant is. So here we are. The smaller amount of product is my answer because it tells me that my limiting reactant is magnesium. That's what I'm going to run out of. Oxygen is my excess reactant. You could not determine that based on the grams that you started with. I know some of you are looking at it and you're saying, well, I started with less magnesium, right? I only started with 1.68. I should have run out of that first. That's a coincidence. It will not always work out that way. The smaller amount of product determines your limiting reactant.